Have you ever stopped to think about how science actually describes the world? Well, today, we're going to crack that code. We're talking about the universal language that scientists use to explain everything, from the tiniest particles to the most massive galaxies. And trust me, by the end of this, you're going to be speaking it fluently, right? Think about it. If someone says an experiment takes a long time, what does that even mean? Should you wait for minutes? Hours? Days? These kinds of words are just too vague. They're subjective. And for science, that's a massive problem that had to be solved. And here's how we solve it. We get precise. Instead of just saying a box is heavy, we say this box has a mass of 20 kilograms. You see that? It's not just a number, and it's not just a unit. It's the combination of the two, the value and the unit of measurement. That is the absolute core of what a physical quantity is. So here's how we're going to break it all down. First, we'll see why physics absolutely needs numbers. Then we'll dive into the universal language scientists agreed on, the SI system. After that, we'll learn its 7 fundamental letters, the alphabet of science. We'll see how to build bigger ideas, or words, with those letters. And finally, I'll show you a kind of secret power this gives you to check your own work.
All right, let's get right into it. We're starting at the very beginning, with the basic problem: why words, by themselves, just aren't good enough for doing physics.
So this brings us to the official term for what we're talking about, a physical quantity. In Italian, a grandezze fisica. It's basically any property of something that you can actually measure, like its length or its mass or its temperature. And here's the golden rule, the one you can never break. It always has to have 2 parts, a number followed by a unit. Saying the answer is 10 is meaningless. 10 what? Saying meters is also meaningless. How many? You need both.
Okay, so we need units. But which ones? My foot is a different size than your foot. So if we measure in feet, who's right? To stop all that chaos, the entire scientific world had to come together and agree on one single system for everyone.
And that solution is the International System of Units, or as pretty much everyone calls it, the SI system. This is it. This is the official language of science. It guarantees that a meter measured in a lab in Rome is the exact same length as a meter measured in Tokyo or even on the International Space Station. It's truly universal. Now, I know what you're thinking. Oh, great. I have to learn a whole new language. But here is the amazing thing. The entire system, this whole language for describing the universe, is built on just 7 basic ideas. That's it. You can think of them as the alphabet of reality. And these are what we call the fundamental physical quantities. They are the 7 pillars that hold up everything else in the world of measurement. Every other possible thing we could ever measure is just some combination of these 7.
And here they are, the magnificent 7. This is the whole alphabet. Everything starts right here. You've got the big 3 that we use all the time: length, measured in meters; mass, in kilograms; and time, in seconds. Then we have 4 more that you'll see constantly in physics and chemistry labs. Temperature. Now this is important. Its SI unit is the Kelvin, not Celsius. Then there's electric current in amperes. For chemistry, the amount of substance is measured in moles. And finally, you have luminous intensity, which is really just a precise way of saying brightness, and that's measured in candelas. That's it. These 7 are the bedrock.
So if those 7 units are our alphabet, what happens when we start putting the letters together to form words? Well, that's how we describe more complex things. And these words have a name. They're called derived quantities. They aren't fundamental on their own. Nope. We create them by multiplying or dividing the fundamental units we just learned. Let's take a super simple example. Area. How do you get it? Well, you take a fundamental unit, length, which is in meters, and you just multiply it by another length, also in meters. What do you get? Meter times meter gives you square meters, or m squared. Boom! You've just created a brand new derived quantity. Or how about another one? Density. That's just how much stuff is packed into a certain space. To get that, we take a fundamental quantity, mass in kilograms, and we divide it by volume, which is itself a derived quantity, meters cubed. The result is a totally new derived quantity, density, measured in kilograms per cubic meter. And we can just keep going. Volume is length times length times length, so meters cubed. Velocity, that's just how much distance you cover in a certain time, so it's meters divided by seconds. As we just saw, density is kilograms divided by meters cubed. The incredible thing is, with just those 7 letters in our alphabet, we can build a vocabulary to describe almost anything, from the speed of light to the density of a neutron star. Okay, now for what I think is the coolest part. Once you understand units, you get this secret superpower. It's a way to check your work in any physics problem that seriously feels like a cheat code. It's called dimensional analysis. Dimensional analysis is really just a fancy name for a simple idea. You look at the units, the dimensions, in any equation you write. And if the units on one side of the equal sign don't match the units on the other side, your equation is flat out wrong. End of story. It's basically a grammar check for the language of physics. So let's put it to the test. Imagine you're rushing through an exam. You've been scribbling away, and you end up with this formula. Velocity equals mass plus time. Before you even think about plugging in numbers, you should ask yourself, does this equation even make sense? No way. It's complete nonsense. And the best part is, you know it's wrong without doing a single calculation. The units themselves scream that there's a problem. And here's why. The unit for velocity is meters per second. You can't add that to kilograms, the unit of mass. It just doesn't work. It's like trying to add 5 apples to 3 seconds. The result is meaningless. The same goes for adding meters per second to just plain seconds. The units, the dimensions, don't match across the equation. And if the units are wrong, the physics is wrong. It has to be. And this brings us to probably the most useful takeaway from all of this. Seriously, before you ever start punching numbers into a calculator for a physics problem, just take a second and check the units. Make sure you aren't adding kilograms to meters per second. This simple little grammar check is your #1 first line of defense against making a mistake, whether it's on your homework or especially on a big exam. So there you have it. You now know the alphabet of the universe and the basic grammar for how to write its language. You have this incredibly powerful tool to precisely describe the world around you. So the only real question left is, what are you going to do with it? What new questions will you be able to ask now?